Hello everyone and welcome to our in-depth concept on free body diagrams. So, as you mentioned in the last video on the intro to free body diagrams are 2D representations of forces acting on an object. And these objects are always represented in the form of squares. So, now how do we show the forces acting on that object? So the forces acting on the object, excuse that it's slanted, there's always going to be arrows that represent, for example, gravity or Fg. If it's on a surface, let's say that this was sitting on a table, let's just put like this surface here. The table would be exerting a returning force due to the third law of motion, which is the normal force. So we're going to be drawing another arrow here of equal length, Fn. Let's say I push the object towards the right, so the force is a rightward force. That means the arrow is going to be stemming from the right side, going here. This is our applied force since we are applying the force. And of course, if we're told to consider friction, we need to make a returning arrow here in the opposite direction, which is f small f, or it's also accepted to just make this curvy f. So those are how we write different forces. And why is it important that we know how to write them properly? Okay, if you notice, a while ago I mentioned something about making the arrows equal in length. This is actually a crucial part of free body diagrams because the arrows also represent whether or not a force is equal to one another. So let's say I'll make another drawing here. I'll make a box that's hanging from a tree. So let's say this box or something, let's say it's hanging onto a tree by a rope. And if it's hanging onto a tree by a rope, that means there's a tension force going up, okay, upwards towards the tree. Wait, let's use a blue one. Okay, there's an upward force caused by the tension of the rope holding the box towards the tree. Now, if this tension force is less than the force of gravity, which we can represent by making gravity larger, so that's going to be Fg, then that means that we can tell from this free body diagram the rope will actually break or the box will succumb to the force of gravity. That's because the force of gravity is stronger than the tension force of the rope. So that's why the length of the arrows are actually quite important. They allow us to determine what is going on within the object or around the object. So let's try and make free body diagrams without solving first for the magnitude of the vectors in the next situation. So I have some practice problems here. Let's try the first one. So a book is at rest on a tabletop. So this one is quite straightforward. First, let's draw the tabletop. I mentioned also in the last video that in every free body diagram, there are essentially three parts. So there's going to be the surface, the box itself, or the square, the object. And there's also going to be the vector arrows. So let's make the book a square since that's how we're supposed to make our free body diagram. So the book is at rest on a tabletop. When an object is at rest, according to the first law of motion, the forces have to be equal or balanced. And how do we know if the forces are balanced? That's if, of course, the sum is 0. So without giving values to our vectors here, let's try and determine first what are the forces acting on this object. So we'll use yellow this time. The book is at rest on a tabletop, and gravity does not disappear, and the book has mass. So that means that the most basic force acting that is acting on the object is gravity, or yeah, the force of the gravitational force, which can also be called weight. So its weight is going down, and this is Fg, or if you guys want the formula, it's mass times gravity. Now, according to the third law of motion, there is actually also a returning force, the force of the table onto the box. So since the box is pushing on the table pushing the box, meaning that there's an upward force. However, also according to the third law of Newton, that returning force has to be equal and the opposite. So as you can see here, we've already made it opposite, and now we just have to make it equal. So since these two arrows are essentially they're basically the same length, we now label this as the normal force. This will also be equal to essentially just negative mg. Take note that this does not change our value actually, because gravity in and of itself, like the acceleration due to gravity, is negative. So negative times negative, this will become positive. And that's how we make the free body diagram for a book that is at rest on the tabletop. There is no applied force, so we cannot have any arrows going here. There is no applied force, or it's not moving at all, so there is no friction. And yeah, so we'll just leave it at that. Now, how would we make them have magnitude? So let's give a mass to the box. Let's say that this box is 2 kilograms, and use gravity, wherein gravity is equal to 10 meters per second squared. I've given us the formula to solve for this. So let's try and figure out first the downward force, or its weight. Since we know that the normal force should just be the opposite sign, or the negative of the weight, then we don't really have to solve for that one anymore, as long as we solve for our weight. So weight is equal to mass times gravity. Let's plug in our values. So we have 2 kilograms times 10 meters per second squared. Now using these values, let's rotate this a bit. Okay, using these values, we'll get 20 kilograms times meter times meter per second squared, or simply put 20 newtons. So this vector here on the bottom actually has a value of 20 newtons. And we used Newton's second law of motion for this, since this is also essentially force is equal to mass times acceleration. And since this is supposed to be equal and opposite on the top, we're just going to do... Oh, oops, it got grouped up over there. Hold on. Okay, there. So since this is supposed to be equal and opposite, this is supposed to be negative 20 newtons, since this is negative 10 meters per second. We're just going to make it positive here on the top, 20 newtons. And now when you add these two forces together, these will cancel out. 20 plus negative 20 is equal to 0 newtons. And since the summation of these forces is 0, we know that the object is at rest, just like it says in the question. So let's try another one. Oops. Okay. Let's just squeeze this in here a bit. Okay, there. A gymnast holding onto a bar is suspended motionless in the air, and the bar is supported by 2 ropes that attach to the ceiling. We have to make a free body diagram of the forces acting on both the gymnast and the bar. So this might be a bit confusing if it's your first time trying out making the free body diagram. But don't worry, it's actually a lot simpler. So let's first sketch out or imagine what the situation would be like. So it says here first that the bar is supported by 2 ropes that attach to the ceiling. So in other words, in real life, it would probably look like this. If this is the ceiling, there is your person over here. There is a bar. and there are two ropes connecting to it. Now, if the person is hanging onto the bar, that means they're part of essentially this system. So their hands are here. Yeah, I'm not very good at drawing, but you guys get the idea. So we have to make a free body diagram of this entire system. And seeing as I've just made that rectangle, I think you guys can see where we're going with this. So our rectangle from this situation would be encapsulating the entire bar and the person. And since we already have this, we can actually just shrink it. So now let's remove our visualization, and we'll use that version for our object. So our object now, this rectangle over here, or rather, let's just make it a square so that it's simpler. This square will be both the person and the bar. And there are two ropes attached to it that go towards the ceiling. Now, whenever there's a rope, there's going to be tension. So a rope always means tension. FT means tension, okay? So since there are two ropes, there are two tension forces. That means there's two forces going upward. So there's one going up here, and then there's another one on the other side. Since it's supported on both sides, they're supposed to be equal. Okay, so this is a tension force, this is also a tension force, and of course, never neglect the gravitational force, which is going down. So now, that is actually our free body diagram for this situation. And this is how you're supposed to approach situations that involve essentially quote-unquote two objects. So in this situation, we have the two objects being the gymnast and the bar. You're supposed to make the diagram of both of them, so just put them in one rectangle. But it's important, of course, that you're able to imagine the situation first, because you're not going to be able to reach the conclusion that, oh, there are two ropes here on both sides and there's going to be gravity on the guy. Because what if the person is not suspended in midair? What if the person is just on the floor? So that means there would also be a normal force up here. So that changes the whole situation. So understanding first the question is definitely a must before you create a free body diagram. So the next two examples are very similar to one another. I'll put them like right above one another so that we can compare. A rightward force is applied to a book in order to move it across a desk at constant velocity. Consider frictional forces and neglect air resistance. And the bottom side is the same, however, it has a rightward acceleration. So what makes them so different? There's constant velocity here on top, and there's going to be an acceleration here at the bottom. How do we display that in a very similar situation? So first, let's try making the most basic part, which is just the box, the book rather, and the table. So we'll just go ahead and make our object. Let's make it purple this time. Okay, so we can see already that the desk itself is made, the object is made, so now we're just lacking our forces. Now, in both situations, there's going to be gravity and a normal force, of course, because the box is resting on a surface. So wait, let's make this over here so we have space for the arrow. Same on this side. Okay. So our normal force and our gravitational force, we can illustrate that first. We'll just make the arrow going down. FG. This should be equal. Just imagine that that's equal. I'm not really good at drawing. Normal force. Same here. Normal force. And here, force of gravity. And now, this is how we're going to handle the two new differences, which is the acceleration and velocity. According to the first law of motion, an object with unbalanced forces will not be in the same state that it currently was. But an object that has balanced forces will continue to be doing whatever it was doing until an unbalanced force acts upon it. That applies for objects at rest, and that also applies for objects in motion. So an object in motion or in constant motion, constant velocity here, means that the forces on it are balanced. So let's say that we are the ones applying the rightward force. That means there's going to be an applied force to the right. Applied force. Now this applied force must be balanced on the other side in order to achieve constant velocity. That's according to, again, the first law of motion, since balanced forces will leave an object in the same state of motion. So our contradicting force here, or one might say the consequential force to it moving, would be friction. These are equal. Everything is balanced here. Since we don't have any values of mass, and it's going to be a bit complicated to cover right now in one video, we're just going to assume that all of these forces now have a sum, or a force sum of 0 newtons. So they are balanced, and now they're all going to be going the same way, constant velocity, forever. Well, not really forever. Obviously, it will stop because of frictional force. But that's how you're supposed to illustrate it, considering that it's at constant velocity. In a real life situation, of course, the book would eventually slow down. And that's because of friction itself. However, just for this situation, this is the correct answer. If you guys want to see like the better drawing rather than mine, because I'm not really that good at it, I'm going to put the link of the site where I got the questions from in the description. So yeah. Now let's try and cover the other part. So a rightward force is applied to a book in order to move it across the desk with rightward acceleration. So the difference here now is it's no longer constant velocity or constant motion. That means now there is going to be an imbalance. And another way to think about it is friction cannot keep up with the applied force. So we're overpowering the friction. Because if we're underpowered and we cannot get past friction, then obviously the box won't move. If we're able to go just the same, just equal to friction, then it's still not going to move. It's still going to cancel out. Being greater a little bit would mean that it's going to be finally moving or accelerating. So we have to show acceleration using the arrows. So let's start again with our applied force. That's going to be the bottom line here. We will always have an applied force. Now, so let's draw the arrow here. Our applied force to the right. Oh, it's still on the yellow. Okay, it's fine. And let's make friction a smaller arrow. Because like we described earlier, friction is getting overpowered by our applied force. So this is how we're going to show that it's accelerating. The applied force is greater than friction, so it's essentially moving faster and faster. And yeah, so that's basically the difference between these two questions. Again, there are balanced forces acting here. Therefore, the law of motion, the first one, is going to be displayed. The object that's in constant motion will continue to be in constant motion. And how do we change this if in a real life situation? We can imagine this to change if someone suddenly, let's say, pushes the box to the left. So if I decide to push the box to the left, I mean the book rather, then that would obviously make it no longer constant velocity. And here for the bottom part, the desk, moving it across the desk with a rightward acceleration, we're moving it faster than friction can keep up. So the arrow of the applied force is larger than friction. It's important to note also that in questions regarding an object on a surface, if the object is not angled, like let's say there's no slope like this, the normal force and the gravitational force will always cancel out. Because the gravitational force and the normal force. They're basically just additive inverses, or they're really just inverses of each other. So this is going to be a negative sign, this is a positive. So that's pretty much free body diagrams. And there are definitely more topics regarding this, particularly now about dynamics. But this essentially covers the simpler ones, the ones about how to just tackle and draw the most basic of it. So we're going to cover more free body diagrams on the topics on dynamics itself, which cover situations such as boxes on an incline, or other systems which have, for example, a box suspended by a rope which has another box suspended to the box by another rope, which might be hard to imagine now, but of course with practice I'm sure you guys can get it. So I've only actually covered 4 questions from the source that I have, the resource that I have, so feel free to try all the other ones in the link, using the link in the description. Those will definitely help, because the more practice you guys get on making free body diagrams, the more natural the ideas and the drawings will come into your mind. So yeah, that's all, and I hope everyone learned something today for free body diagrams. After this video will be the in-depth concept on dynamics itself, so please don't miss that, since that will also be the integration of the laws of motion, such as the law of inertia, law of acceleration, and the action-reaction law. So thank you everyone, and I'll see you in the next in-depth video. Goodbye.